Hey guys, is the volume working? Okay. My name is Boris Lipchin. I'm at MIT right now with the Space Systems Lab and work for Dr. Oliver Senzatero. My previous life I was a flight software engineer, so I pretty much didn't deal with any other type of fault tolerance other than something that was related to software computers. Since then I've been told that there are other types of fault tolerant systems, but this is flight software, so I'm among friends now. So, okay. This is basically my research. I'm going to start by talking about fault tolerance objectives and like what's the whole point. Then I'm going to kind of discuss what I mean when I say software-centric fault tolerance, and just sort of talk about this prototype that we're building. Then I'm going to kind of dive into some of the details and talk about some consensus protocols and why that applies, and just discuss some future work. Okay, so in general, I'm sure this is all very obvious to you guys. Space is like the worst place to store a computer in general. Getting to space, also not great. There's also seems to be a growing kind of discrepancy between the capability of terrestrial computers and sort of ones that are radiation hardened. And occasionally there's like discrete events where they bring back radiation hardened computers to be kind of almost as good as terrestrial ones, but this requires like substantial effort on the part of like one or two companies, and so we believe a more kind of maintainable path forward is just to be able to use terrestrial computers for everything. And so this is kind of, since our research is about trying to make kind of how to engineer space systems cheaper, we started looking at fault tolerance. Sort of like fault tolerance is great. Really, it's frequently a requirement for NASA. But kind of the main takeaway is that you're effectively trading money for mission lifetime and reliability. So that's sort of like the trade that we're going to really focus on here. It's not a really great trade sometimes. It's very expensive. Fault tolerance, kind of you get diminishing returns very quickly, very fast. As systems become increasingly complex, reliability actually is going to go down. So your mileage may vary, kind of situation. And kind of one interesting thing is that there's a lot of academic and kind of small missions where fault tolerance is just not an option, because it's, you have to design a lot of hardware that's kind of, that's custom. You have to design some software that's also custom, and you just don't have the money. And frequently maybe you don't need to, but if you could have a cheap option for fault tolerance, we're kind of interested in what would happen. So we decided to look at software-centric fault tolerance. So just really fast, what kind of the philosophy that we're using here is that software-centric fault tolerance considers, and you could kind of push and pull this definition a little bit, but really what I focus on is the execution of a process, or a thread, but really a process. And then the process at the end of the day has some capabilities that it runs an integrator for your IMU, or maybe it looks at some science data, but at the end of the day it has some product, it has some output, the output vector maybe even, that goes to your system. And like one way to think about it is if for whatever reason a fault happens, you can't run this process anymore, you've lost some capabilities effectively. So, and maybe starting to run this process again at with a state that's basically synchronized to all of your other redundant processes that you're running to enable your fault tolerance, you've like recovered that capability. Now this fault could be that you lost power to your computer, so there is no more computer to run the process, or maybe you've suffered like a transient fault in your LU and your adder like gave you some garbage, and now you're like operating on crazy data. But it really doesn't matter. The point is that the whole goal here is to maintain processes running at the state that you want to run them at. So here the goal is basically to create a cheap version to fault tolerance, and I'm sure you guys have all heard this like 2 a.m. before like your release or launch or whatever, that you hear like, oh, just fix it in software, and so this is basically that approach, like can we fix as much as possible in software, because we believe that might be a cheaper approach. And software, kind of being the magical thing that it is, you can try to make it as generic as you can. The goal here is to make it as generic as you can without making it so generic that it's like completely useless for any real flight application. And we can talk about the assumptions that we've made in a second later, and we believe they're reasonable assumptions. But really, the idea here is that it would be nice if the flight software engineer could just write flight software that was completely agnostic to the fact that it was going to be run in a redundant manner. And this way, you could provide n fault tolerance, where n is sort of depending on how much money you happen to have at that time. Maybe, for example, you fly one mission that was like testing like a technology, like testing mission on a very small satellite platform, and then like it works, and then 6 months later you want to fly it on a much larger platform, but that's going to have a longer mission time. You're going to want to have more fault tolerance. You can just sort of like, other than sort of the overhead costs of having more hardware in the rocket, more interconnect between your flight computers, whatever, maybe it would be nice if there was no added pain sort of to implement it. And you get sort of like all the kind of added benefits of having a more generic system that you test once and fly many times and stuff like that. And your flight software engineers might have a little bit of extra time, which is pretty awesome. Sort of like the drawback is that it does not actually give you fault tolerance. What it does give you is it sort of moves the problem for where it's cheap to where it's rather expensive to solve to where it's cheap to solve. At the end of the day, you're going to have like a bunch of redundant like avionics boxes. They're going to produce some output. Something, since you're probably not going to have redundant actuators or as many redundant actuators as you have computers, whatever, you're going to have to sort of mux that thing together. So you're kind of like delaying the problem, if you will. You're not really solving it. So then you're like, what's the whole point? Why do this at all? The nice thing is that what you're putting is you're solving the problem where it's cheap. You're kind of restricting the fault tolerant, the rad-hard hardware to like a part where it's a relatively simple part of the system. It's just sort of reading some output vector. Maybe it's just some gates that are going to do some voting. Maybe you do put a RAD 750 in if it's something more complicated, but at the end of the day, your main flight system, the one that's doing kind of all the complicated stuff, you're using terrestrial computers. You have lots of resources to play with, and that's where you're going to get most of your requirements drift and stuff like that. And that's, as David pointed out this morning, margin is everything. So you're going to want margin there. So this is, at the end of the day, this is sort of a net win in general, we believe. And so just real briefly, what I mean when I say a flight software process. It's something that runs in a cycle. There's, it reads some inputs from sensors, has some internal state, and it executes some function, and then, a series of whatever, does some calculations, and it creates an output. It's very simple. The kind of important takeaway here is that the whole idea is that the function, the computation that it executes, for us, and this is basically the main assumption that we're making, is the inputs and the internal state vector to your process, the computation that leads to outputs has to be idempotent. Basically, the whole idea is that if you run that operation at different times or repeatedly, you're going to get the same output. And this seems like very reasonable, but actually there's a few complications as a result. You can't have any source of randomness inside your flight software. You can't reference any sort of hardware-specific things. Like you can't have you can't look at your system clock time internally very much. So there's generally, it's a fairly reasonable thing to ask. You might have to modify your flight software a little bit to get it to work. And just one more, and just kind of to reiterate, the whole point of software-centric fault tolerance is to maintain internal state in a process. That's kind of the last bullet point. And we believe that if you somehow magically do that, then life is okay. So what did we build? We're in very late stages of implementing our prototype. We have it's a C++ library. The whole idea is that it's kind of designed with avionics engineers in mind. It links against your flight software stack. There's a fairly reasonable expectation for the interface that your flight software stack exposes. That's just to be able to get and set inputs, internal state vectors, and outputs. Now, again, obviously, for some of these bigger missions, your internal state vector, you're Jesus Christ, that's a lot of things. So it depends on how you've written your software, but in certain software systems that might be easier than or harder than others. And maybe it's some of you might be 100 megabytes, but if it's a reasonable amount and you've somehow managed to kind of assemble it in one place, this is actually a fairly easy thing to do. We also don't have any fun backronym that's very common in academia. So if you guys have any suggestions. There's Boris's software-centric fault tolerance thing isn't catching on. So some more assumptions that we've built into our system. So we require you to have a fully connected peer-to-peer network. That's actually not, we can relax that requirement. It's just that if you do relax it, the statement of how fault tolerant you are becomes kind of a complicated thing to answer. So we just say peer-to-peer, fully connected network. And since you're plumbing kind of effectively mission-critical data through your network, there's some implicit bandwidth and stuff requirements. Like I said, you need to have very defined inputs, internal state, and outputs for your vector. Basically, for your system, rather, to the point where if you have and to the point that like saving that state is actually valuable for you, right? If you have like some satellite whose attitude is important, and all you're doing is saving some like their battery charge data, but not its attitude, then the system isn't very useful. Like you really want to put attitude as part of the state. And we require some process level time synchronization, which is it's sort of like not in the scope of this talk, but that's very relevant. That's very necessary to get like all our consensus algorithms working and such things. But we're going to kind of implement that. We're just punting on that right now because we don't have time. Anyways, capabilities. So one thing that we don't require is we don't require your system to be homogeneous in any way. So you can, for example, which is kind of a common problem for some of these like more like typical flight software like fault tolerance things. You can actually run 3 different binaries. As long as somewhere deep inside that binary, you're still like running the same kind of computational kernel to like where you're integrated or whatever have you. We don't actually care as long as you're doing the right thing. We don't care how you're doing it. So, for example, if you have like if you're running if you have some flight systems, you've got 3 flight computers, and one of them you've got some kind of standard set of sensors attached to every flight computer, like an IMU and a star tracker or what have you, and then one of them has a telescope attached to them because like connected because it's a science mission of some type. You're gonna maybe you read that data from the telescope in the same binary. So you're running physically different software and it's compiled in a different way, but we don't care as long as you expose your state and your input and output vectors in the same way. We don't actually care. And so that obviously same goes for the hardware. It doesn't matter, you can compile different targets as long as you meet sort of some performance requirements for the network and the hardware. Nothing actually matters, which is sort of the nice thing about software. And also, so generally NASA defines, I believe, faults as you can only really have one fault at a time within some reasonable amount of time, and what is a reasonable amount of time is somewhat ambiguously defined by NASA, but generally, so we can handle one Byzantine faulted node at a time, and then there's multiple hard faulted or fail silent nodes that we can handle. How many, it's sort of it's kind of a slightly complicated discussion, but generally we can basically we can abide by sort of NASA's Byzantine fault-tolerant requirement and we can recover nodes with, well, how fast we can recover nodes is sort of a function of your system, but we can. Just generally what happens, you've got a series of however many nodes you have, like how much end fault tolerance you chose. You read some sensors. You run this thing called a series of consensus protocol instances. And what that does is basically the end result of this process, of this kind of part of the system, is that every node that is healthy should know about the input state and an internal state of every other node. And so that's sort of like, and I'll talk about what consensus means in a second. That's like a computer science-y kind of concept. But the whole idea is that everyone knows what everybody else is thinking at this point. And when I say, just to kind of clarify, the way this happens is that consensus protocol, there's the way we've implemented it, there's one primary, and then the primary kind of shares its state with all the other guys, and they reach consensus. And so basically, in order to do this, there's like a time-triggered kind of like system where A runs like time 0, and then A is primary, and then it tells everybody about its state, and then B runs, and it's primary, and tells everybody about its state. And if A doesn't run in time, that we just consider that basically like, oh, you've failed. So nobody gets to know about what A was thinking, and that's fine. That's just the one failure for that cycle that we can handle. Then they basically, so everybody knows everybody else's state. Then they effectively internally vote on what internal state to use. Sorry, it's kind of bleeding off the edge of the slide, huh? What internal input vector internal state to use. Since everybody's operating the same data and running the same code, they're going to reach the same answer. And so then they run the consensus protocol again. They share their outputs, and then and then they output their voted output that they all decided out to the output voting hardware. Actually, the second consensus protocol thing is kind of extra. I've put that in there just to detect errors in calculation along the way. In the final version, we might actually take it out because it just wastes resources. But sort of depends on how we do fault detection, which again is sort of like outside the scope in a way. But anyways, regardless of sort of where you have faults along the system, if it's before a consensus protocol, one of these little clouds, basically the consensus protocol with the voting will effectively mask that error out for you, and then, or if it happens at the very kind of the last mile right before the output voting hardware, which is your rad hardened hardware, that's still the error, because we assume you only have one fault per of your active nodes per cycle, it's still going to be voted out, so you're in good shape. So that's generally how everything works, and I'm going to talk about kind of what and I think this is fairly straightforward, but the clever bit is kind of baked into the consensus protocol. So consensus is like, I don't know if you guys have done this, it's like a real computer science-y thing. There's like the last Turing Award went to Lamport for his work on consensus. There's Paxos, I think for Paxos specifically, so Paxos is a non-Byzantine consensus protocol. There's like a whole set of Byzantine consensus protocols. Generally, it's a way to sort of in the presence of faults and potentially faulty network for everyone to agree on one value. So just without, it's, yeah, and a nice thing about handling Byzantine faults is in general it sort of envelopes other types of faults. So if you can claim that you're kind of Byzantine fault tolerant, you've just kind of won all discussions. So generally, like just to give you an idea of what a Byzantine consensus looks like, they make statements like we've got 3 f+1 nodes where f is the amount of failures, simultaneous failures we can handle. There's typically most Byzantine protocols consensus protocols have they use some form of encryption, which generally there's some public key thing. There's I think PBFT uses this thing called message authentication codes. Generally, the whole idea is that if node A tells node B that node C sent it a message, it can provide that message and then it can't fake it. So everybody, you can't basically tell other people that you were told something without having been told that value. So you can there's a lot of, and that's pretty key to most Byzantine algorithms. Anyways, it works just I'm not going to waste a lot of time on this, but anyways, there's a kind of multicasts a message saying hey, I believe value X is important. There's a retransmit and another retransmit, and they're trying to basically, and eventually it goes to the client. There's a good reason for each of these, and there's you require some amount of messages at every step that are authenticated to make it. But the point is that they're basically building these things called replicated state machines. There's this very kind of big, kind of interesting, very rigorous thing that they're trying to build, but we don't really need a lot of that because we're making a lot of assumptions about when we're going to reach consensus and when we need to run. So there's these things called views that they use when your primary fails and stuff like that. You need to you need to decide that, okay, my primary's failed, I'm going to use a different primary. We don't really have a client because we just want these peers to know about the status. So there's basically a lot of layers that we can take out. And we're saying we're only going to handle one simultaneous Byzantine failure at a time, which gives us a big win generally. So there's a large amount of heuristics that we're taking advantage of here to basically kind of whittle down these Byzantine algorithms into something really, really tractable, something fast that you can run on your system. And so we're kind of we're using this as inspiration, but really we're building something completely different. But it was instructive, I think, to see. I hope. Yeah, and so the whole general idea for us is that it's very simple. We have a primary, so let's say if you've got a 3-node system and in a given, you're going to share state 3 times, where A has to tell everyone about its state, and B will, then C. So this is just the A bit. So A basically multicasts its state to its peers. Its peers share that, cryptographically authenticated propose and in a message called an accept that contains this proposed message. And then if a majority of the nodes receive correct accept messages that all have the same propose inside there, they okay, we've reached consensus on the information that A has. So the main kind of thing that they know after this point is that, for example, if B reaches consensus on A's state, what it knows is I know what A's state is, but I also know that everybody else knows what A's state is. And that's kind of the key thing here. Just kind of some random details about some of the heuristics. If you're a primary, you just transmit state, and then you just wait for a majority of accept messages to come back to you from your peers. On the peer side, if it's very simple, if you get a proposal, if it authenticates, you transmit accept messages to your peer, and then you also wait for a majority of accept messages to come back to you from your peers. If for some reason you got an accept message, but you never got a prepare message, there are certain fault modes. Again, this is if you have some network failures, for example, if you don't have a fully peer-to-peer connected network, you might get into these cases, or if you have some, any number of packet loss or whatever. That's okay because an accept message contains a cryptographically authenticated propose message in there. So you can basically that is an implicit propose in a way, and that's fine because you know that it made it from the right primary because you can decrypt his message. But you can't accept any more proposed messages from any other type. If you get an accept message from a peer that contains a different proposal from the one you've received, that just basically uniquely says that your proposer is doing something very weird, and so the consensus at that time between all the good nodes is that there should be no consensus, which is fine. So at the end of the basically at the end of this. When you run this n times, one for every node, at the end of the day, you will have for example, in the just context of your internal state, sharing your internal state, you're going to have a bunch of buffers. You're going to have n buffers of your internal state, and some of them, if one of the consensus protocols did not go to conclusion, you just say well, I can't vote for that guy. So ideally, all the other ones will be just the same state, and you'll figure out which internal state you're actually going to operate on. But if you didn't reach consensus for one of them, you just suffered a failure in node, and that's fine. You just that's not a valid buffer to vote on, so life is okay. Just sort of kind of a hand-wavy proof why this works. There's basically two cases. There's a bad acceptor case and a bad proposer case. The bad acceptor case is a much simpler one. If C is a faulted node, A transmits 1 to acceptors B and C, like state 1. You can, it doesn't matter, accept transmits something to state B and C, to nodes B and C. B being a good node, it just retransmits, that message and basically transmits an accept to all the other nodes. It has an implicit accept from A, which is kind of an optimization. If you're proposing something, you're implicitly accepting it as well. You can transmit both messages, but it's just a waste of time, and just makes the proof a little bit more annoying. So C cannot fake propose messages because they're cryptographically signed. So it really has one of two options. It can either transmit an accept to one or both nodes, or it can do nothing. But A and B have already reached consensus on one with two nodes in agreement, so it sort of doesn't matter. So life is good. In the case of a bad proposer, this is slightly more complicated. So for example, a bad proposer can transmit two different states to different nodes to try to maliciously trick them into doing something bad. But we can detect the fact that you've got two cryptographically valid messages that contain different information from the same proposer. It means it's crazy, so you can basically drop consensus there. Or alternatively, A can send one of the messages and not tell the other guy, and then in which case B sends accept to its peers. C is gets that proposed message, A's proposed message, not from A but from B, does its own, sends its own accept messages, and then everyone in consensus is reached anyways. So this is also okay. So basically, the only thing that's not okay for this protocol to do is it's fine if A is a bad node for B and C to reach consensus. What's not okay, or everyone either has to reach consensus together, who is good, or not reach consensus together. The only thing that's wrong is for some of the nodes to reach consensus while others should not, among the good nodes. So that's would be a failure of this protocol. And if you think this can do that, you should tell me. I'm pretty sure so anyway, so the whole idea is that this system they're building, that we want to provide, so n-level fault tolerance. You're building a system, you basically send it a configuration file that's saying, okay, I've got these 3 nodes, or I've got these 10 nodes, these are their IPs, or whatever addressing system you're using on your, whatever your depending on what your network is. Network and, bandwidth and stuff like that are, limiting factors. And, but the whole idea is that you kind of make it very easy for the flight software engineer to determine what level of fault tolerance you have based on how much money you happen to have that day to buy hardware. This is very flexible to a variety of software and hardware architectures. We believe that so the whole point of this is to sort of determine how good our assumptions are. So we've made a bunch of assumptions about what your hardware and software looks like, and we want to sort of float this system on a couple of internal projects at the lab and see if if we've made reasonable decisions. We effectively kind of protect against transient faults very readily by rehydrating the state every cycle. So if you shut down, if you reboot a process, it reconnects to its peers. There's the time synchronization protocol has to resynchronize it, which I did not talk about here, but it will. And then it gets the state at the beginning of every cycle, and then it has its own state, which is garbage, and then it has n-1 states from all its peers, and so we'll vote for that state, and then basically just get right back into the group and keep chugging along as if it hadn't done anything. We can Also, you could even hypothetically protect against hard faults. You can imagine a system where you launch a satellite that's got like n nodes that are powered off and n nodes that are powered on, and as you reach some total dose, of radiation, you actually just power cycle. You just rather permanently shut down an active node, and then bring up one of your inactive nodes, which probably has, which I think some research shows that they're generally less, affected by total dose radiation if they're not actually running. And so you can bring back one of your computers that's just a cold backup and say like, hey, you're like node 3, and then goes like, okay, and it like joins joins kind of the quorum and just starts going along. So you could actually potentially extend life cycle of your satellites by using this like fairly dumb like software system. So really the thing that we need to do is, well, first of all, we need to build this Byzantine time synchronization system. But we also need to kind of the result of the research, we hope, is basically to propose like this is how many megaflops per dollar you have. So you have like if you have you want to have an n fault tolerant system and you have this much money, roughly given a bunch of like assumptions of varying quality, how much like computation can you do in your system? And you can compare that to like a Radstone 50 solution, and you could say whether our research is worth anything or not. So there's a bunch of like automatic characterization tools in order to determine just like that would be really helpful for the flight software engineer to basically say like, oh, can my network handle, I've got like an input state vector of this size and an internal state vector of that size, like can this even work ever? So that would be like, so characterizing a system readily is something that I think would be very helpful. And just basically showing how, like, we kind of envision that network bandwidth is actually going to be, like, basically the bottleneck for most of these systems. So just showing how network bandwidth, versus computation, like, affects the, how possible it is to build this would be kind of the result of the research. And I think that was fast, but that's it. And I don't have a question slide, so you're going to have to just ask them right now.
Other questions? Yeah.
Are you just going to implement NNTP for your protocol built on top of this for your Byzantine time synchronization? Is that what you're going to do, or how are you going to work that?
I don't think NNTP. I was looking at a Byzantine fault-tolerant time synchronization protocol that I don't think NNTP is, if I'm not mistaken. So that's probably what we'll do. I need to get a lot more familiar with that. But yeah, because I mean, if we claim Byzantine fault tolerance, if time synchronization isn't Byzantine fault tolerant, we don't actually have anything. So like the time synchronization has to be at least as good as the fault tolerance, like that we can produce in the system. So, but we'll probably implement a few of them just to test them out.
Others?
Too late.
Oh, way up there in the back, there's a question.
We don't have enough viability.
So I believe you said you were working on a project for this currently. Do you guys have just like a test database that you can run some of these simulations through, like the Byzantine analysis, or?
Okay. Are you asking like how are we testing this? Like what the hell are we doing?
Questions are terrible today. Do you currently have just like a software in the loop test bed to kind of assess a Byzantine setup? Because remember correctly from the start, this is a somewhat different software setup than what would normally be done.
Yeah, so what we have is, I think, considerably more ghetto than what you're imagining. So since this is like just a pure research project, and the way we're going to basically simulate Byzantine faults is there's going to be hooks into this software that will simulate, that will basically, like, you can tell a proposer, okay, lie. So like, and he's going to sign different messages and send it to his peers and stuff like that. So and this is maybe not a great way to test things from like a pure flight system perspective, but yeah, we'll actually mutate the real like flight code in order to prove that it's Byzantine tolerant, because I think it's much easier. Also, there's I'm going to try and effectively like just twiddle memory and stuff like that. And you're not going to really get. It's very difficult to generate Byzantine faults in the wild, so to speak. And like you can like play replay attacks and stuff like that, but really other than that, you're like very limited. So in order to like prove that you're truly Byzantine fault tolerant, we're probably just gonna like mutate the code and have it like tell it like do Byzantine things, and we'll probably just play with memory and just get faults that way as well.
Yes, my question is, doesn't the network have to be synchronous? I guess in terms of Nancy Lynch's FLP impossibility theorem, I thought the network would have to be synchronous.
Yeah, so this is a little bit hand wavy, but so the whole kind of the statement that we're making is that if we over provision kind of the system enough that we're using 10% of the bandwidth at any point, we can make some statistical arguments that the system is not going to basically like have a latency bigger than X, and then we can and you just basically like run your system and you test it in all sort of stress cases, and you look at that data and you say like, okay, we have like a lot of margin on all of the various, there's a lot of, I don't cover this very much, but there's a lot of very kind of subtle places where you have to put margin on times because the system is very sensitive to time. And so we can basically just say like, hey, yeah, we never get anywhere within like 80% of what our margin would have to be. And so like, it is hand wavy, but yeah, I mean, ideally, if you have like some space wire or something like that, you can make some much better claims about how tolerant your system actually is to faults. But I think for the purposes of this, is just good enough to like say like it's we're nowhere near a fault. I don't know if I answered your question. So.
Okay, other questions?
Two questions. One is, what language are you using, like Linux and threads and things, or Golang or whatever? Second one is, what magnitude of, how many different nodes are you planning to do with testing on the order of dozens, hundreds, thousands, millions?
That's a good question. So this is a C, C++ implementation of everything runs on, I haven't run anything on anything other than Linux, but that said, I'm kind of keeping a wary eye towards using anything that might be that might tie us too closely to Linux, just in case. So, I mean, at some point, you're going to have to like interface with a network stack, and I think you make some decisions there. But if it's well abstracted, you could kind of use object-oriented and swap something in. And as far as how extensive the testing is for the number of nodes, maybe not thousands, but yeah, I'm going to probably try to take one of steal some cluster at MIT at some point. And again, like the amount of nodes is. That's one thing, but I think it's probably going to be very sensitive to the network between them. And at some point, yeah, you're not going to have like 20 NICs in a computer ever, or like it's very difficult to at some point the harnessing becomes so heavy for your spacecraft, you're not going to actually it's just not worth it. But just for having like the graph and determining at what point does our system actually start leveling off in terms of how much data you're putting on the wire, it'd be useful to okay, you've got a 10100 gigabit whatever thing. 20 nodes, does it work or not? To see whether the computational load kicks in before the network bandwidth, or basically. But yeah, I mean dozens, I think, but no much more than that. I think it's not useful.
Last question, then we need to go because there's a lot in the building.
I just have one question. So I'm kind of new to the software realm. I'm in spacecraft operations, and so I see what you're doing here, and I'm very confused about what the different nodes would actually be. Like, is there a very simple physical example of an actual spacecraft and how this would work that you could tell us?
Yeah, there's for example, I can tell you Dragon, for example, will have several flight computers, or most Cygnus, I think. HTV, I know, has 5 or something like that. Cygnus probably has something. So they have different nodes, basically, different flight computers that all are supposed to do the same thing. And then in case one of them fails, you have effectively 4 other guys telling you that hey, you're different from us. So maybe you're not going to listen to what you're doing. And so there's downstream actuators that there's some voting logic usually, and then they're gonna listen to what the majority is going to do. Usually it's a lot more complicated than that because of Byzantine faults and stuff like that, but that's generally the idea, is that you have redundancy in your avionics system. And so a node is really, it's just an entity on a network. You could actually run this on one computer, and then if you say hey, I only care about transient faults, I don't care about hard faults, you could actually run this. You could take your iPhone or Android, and you could run 5 instances of your flight software, and then you have like what's called a time. I forget, but it's basically the type of fault tolerance that you recompute things multiple times, and then if you you compare the output of that potentially. So like you could even have one physical box that runs all this. It's just that it's better fault tolerance to run in multiple boxes. So a node is just an entity on a network, effectively, that does a computation.
Very good. Thank you.
Okay.